today, as a part of our subject selected topics in decision modeling, we are going to start a new series, that is on integer programming. So, integer programming is the first lecture. We are going to discuss the introduction of the topic. First of all, in most of the decision modeling problems, particularly when we use linear programming, we have a continuity assumption. What it exactly says, that the decision variables, they are divisible in nature, in the sense that they need not be integer. That means, they can also have what is known as fractional values. So, when there are fractional values, then the continuity assumption holds, but when continuity assumption does not hold, the kind of problems that we get where the solutions are integers, they are actually called integer programs. Now, sometimes what happens, that the problem, the decision problem really does not require any integer values. That means, continuity assumption holds, but there are certain kind of constraints like either or constraints or some special type of constraints, where some of the variables are to be binary. That means, those variables will assume only a value of 0 or a value of 1. So, when you have that type of situation, that means, the value is either 0 or 1, that is binary variables, we have what is known as mixed integer programming problems. Then there are many different real life situations which you really require integer programs. Is it all right? And we have efficient algorithms to solve integer programs. Now, our lectures we shall divide like this, that in the initial part we discuss some integer programming problems. After discussing different types of integer programming problems, we shall see how to formulate integer programming problems, because formulation of such decision problem is a very important exercise. In solution is also very important, but even more than solution, formulation is, I would say, even more important, because unless you formulate, the solution is not even possible. And now there are a lot of mechanization, in the sense that we have software available using which you can solve integer programming problems, but real challenge lies in the practical world. A given situation, how do you model it as an integer program? So, given that we spend certain time on formulation of such problems, and after that we actually go into how to solve those problems. So, that is how we move, that initially discuss certain integer programming problems, then we discuss how to formulate them, and later on we discuss how to solve them. Now, certain applications of integer programming problems. So, here is a list, that project selection problem, which is a type of knapsack problem, where we have a number of projects have their certain input level costs or input level investments, and there is certain amount of return which projects to be selected. This is also a type of knapsack problem, we will discuss it further. The second type of problem that we shall discuss are the fixed charge problems. See, what happens in fixed charge problem, in many situations we see there is a certain amount of charge which is fixed and certain amount of charge that is variable. But then if you do not go into that activity at all, then there is no fixed charge. Is it all right? So, therefore, fixed charge can come only when the variable value is above 0. If it is 0, then that activity itself does not start, and so if the activity does not start, there is no question of a fixed charge. So, how to model such situations and solve? Thirdly, the cutting stock problem. See what happens in cutting stock, usually even take the simplest one dimensional cutting stock problem, we have a certain steel or certain kind of plate of a certain length, but the customer demand is not in that length, the customer demand is a much smaller length. So, question is how do you cut that stock so that we have minimum trim loss. Trim loss is basically the amount that is remaining after cutting off. So, idea is that we decide certain cutting patterns, maybe number of cutting patterns, and the integer programming problem is which patterns to choose. Is all right. The fourth type of problem can be called as set covering problem. We have a certain set and we have to cover maybe all the elements of that a given set, but then there is a criteria, right. The facility has a criteria. So, within that criteria, how do I cover all the elements? We will know what exactly it is as we see one problem. Apart from that, there are assignment problems, like assignment problems where we have a number of machines, number of jobs, and with different capabilities to how to assign a given machine to a given job. So, these type of problems. And then traveling salesman problem, where a salesman moves from a city to a number of cities and it has to go through all the cities exactly once and come back to the starting city. So, what should be the route that the salesman should follow, so as to let us say minimize distance or minimize cost or things of that sort. So, these are some applications. Obviously, these are not the only applications of integer programs, there could be many other applications, but we thought that these applications really give a good exposure to the integer programming problems. Is all right. So, having said that, let us look some of these problems and what are the pros and the cons of such problems. The first one can be called the project selection problem. As I said, it is a type of knapsack problem. Let us say there are 5 projects and each project has a cost and a return after let us say 3 years. Is it not? The costs could be 5,000, 6,000, 3,500, 8,000 or 7,500, and there are different returns. We have with us let us say 18,000 rupees. So, question is which projects will be chosen so that the net return after 3 years will be maximized. Now, I have put a condition here, a project can be chosen only once. In that sense, it is a 0-1 type of integer program, but then you can also have you can choose a project more than once, right. So, that would be a slightly more difficult project selection problem, right. So, you understood that what is a project selection problem. Now, a knapsack problem, as we have discussed previously in our dynamic programming classes, is a knapsack with a total weight restriction, say W, and there are different types of items with individual weight and value. So, you can stack as many of any of these items in the knapsack. So, question is how many of each type of items are to be stacked into the knapsack so as to maximize the total value within the total weight restriction. So, first of all, why is it integer? Because if the number of items or let us say number of item 1 to be taken in the knapsack, number of item 2, number of item 3, they must be integers. Or if you can take only one of each item, then that is a 0, 1, but then again an integer program. So, how the project allocation program or the project selection problem a knapsack problem. What is your knapsack? The knapsack is an imaginary purse where you have your 18,000 rupees, that is the budget, and each project which is like individual item, they have a certain cost and a certain return. The idea is that within those costs, how do you obtain a certain amount of return, maximum amount of return using those 18,000 rupees. Is it all right? So, that is the precise thing that we need to do under this situation. So, in this way, you can say the project selection problem is also a type of knapsack problem, right. So, you have seen that project selection problem is indeed a knapsack problem, right. Now, this is an integer program because a project could be either selected or not selected, right. So, what are some decision variables? The decision variables will be x j equal to 1 if project p j is selected, otherwise 0, is all right. So, x j will have a value 0 to 1, which is like a decision variable if the project is selected. So, that could be our decision this thing. So, what should be the exact formulation? We will not discuss it now, we are just discussing the type of problems that we have here. Additionally, there could be some additional constraints. What are those additional constraints? Something like, let us say, at most 3 projects can be selected. Is it all right? How will you model this? Or if project 2 is selected, then project 1 also should be selected, must be selected. Or if project 2 is selected, then project 4 cannot be selected. So, you see there could be different types of conditions within those constraints, and that would make an interesting integer programming formulation challenge which we may have to solve in such kind of project selection problems, right. Now, let us see another type of problem which is known as the fixed charge problem. So, let us take this problem that there is a garment company and it manufactured 3 types of clothing: shirts, shorts and pants. The machine needed for manufacturing each type of clothing is rented, right. So, you actually obtain the machines on rent, and for each type of clothing you require certain hours of labor, certain square meter of cloth, and there is a sales price, and there is a variable cost, and there is a fixed cost which can be called as the rent. So, how will you formulate this as an weekly profit, so as to maximize weekly profit? So, how will you go about it? You see, there are certain constraints which may be called as a labor constraint or cloth constraint. There is a kind of variable cost and there is a kind of fixed cost, and you can have a profit component also can be obtained. So, what will be our decision variables in this kind of problem? The decision variable could be the number of shirts, number of shorts and number of pants to be produced, and as you understand that these has to be integer quantities, right. So, in that sense we have an integer program. So, decision variables x1, x2, x3, number of shirts, shorts or pants. Now, it is known that there will be no rent for no production. So, if you do not produce shirts, obviously we need not have a machine to produce shirts, and if same thing holds for the other 2. So, question is, how do you consider this fixed charge, that is rent, in the problem, because you cannot hard code it. If you simply add it to your program, there is a fixed cost, then it is not dependent on your decision variable. Is it all right? Since it is not dependent, it is fixed. So, when x I equal to 0, you need not have that fixed cost equal to 0. I hope you understand. Let us see what exactly it means. Supposing we have total cost equal to fixed cost plus variable cost. So, say fixed cost is FC and variable cost is some VCI into XI sum over, obviously we have to sum FC also for different I and sum of VC also. So, this is the total thing, but if you take it in this manner, the problem is what happens when Xi equal to 0 for, let us say, I equal to for all I, let us say, right, let us say for all I Xi equal to 0. Take that situation where you do not produce anything. Then also these term, because this term will become 0 because Xi is 0. So, this term will vanish, but this fixed cost will remain. So, you cannot model it in this manner, is it not? So, this is the difficulty that you are going to face in a fixed charge problem, if you try to model it in this method, is it all right? So, that is the difficulty we are going to have, what is to model a fixed charge problem in this manner. So, having known this, we have to then understand later on that how do I go ahead with such situations. The next one is a cutting stock problem. So, suppose a company produces a wide continuous sheet of material, it could be a steel or film or paper or fabric, and customer demands various width of thinner strips, right. How should you cut the wide sheet into strips to meet demand while minimizing either the amount of raw material cut or the amount wasted, right. So, let us take an example. The customer demand 25 of 3 feet boards, 20 of 5 feet boards and 15 of 9 feet boards. So, and the company manufactures 17 feet boards. How can you minimize the waste? Let us look at this problem carefully, what it really means. You see, assume this is your 17 feet. So, this entire length for you is 17 feet. So, you have a particular what you call width of steel sheet and total length of that is 17 sheet. Now, suppose you decide that I will utilize this entire sheet to cut what is known as 3 feet boards. So, what you can do? You can cut 1, 2, 3, 4, 5. So, this is the first one, this is the second one, third one, fourth one and the fifth one. Each of them are 3 feet. So, like this is 3 feet, this is 3 feet, this is 3 feet, this is 3 feet and this is 3 feet. So, you can cut 5 of them, all right. And what will happen to these remaining 2 feet? This you cannot utilize, it will be your trim loss. Is it all right? So, you understood this problem, and this you can say is one cutting pattern. So, this is a kind of cutting pattern, one of the cutting patterns that you can think of, that you have a cutting stock problem where you have generated one cutting pattern. Can you think of another cutting pattern involving 5 feet and 9 feet? You are correct. You can have another cutting pattern where you have, this is your 17 feet. So, you have 9 feet here and a 5 feet here. So, this is 9 feet and this is 5 feet, and you can have a 3 feet also. So, good thing is this, that with this 17 feet you can have another cutting pattern where you can cut one 9 feet, one 5 feet and one 3 feet. You see, you cannot really have these pattern, this is another cutting pattern. So, this is cutting pattern 1 and cutting pattern 2. So, really speaking, what you can do, you can take a certain amount of cutting pattern 1 and certain amount of cutting pattern 2, and you can decide, maybe you would like to have more of cutting pattern 1 and less of cutting pattern 2, or you can have other type of cutting patterns like 3, 4, 5, etc. So, the real question is, how do I really choose certain cutting patterns in how many numbers, so that we achieve our goal. What is the goal? How to minimize the waste, that means the trim loss, so that we can fulfill the customer demand of, let us say, 25 of 3 feet boards, 25 feet boards and 15 9 feet boards. So, you can understand that here decision variables are how many of a given cutting pattern we need to choose, is all right. So, that is our cutting stock problem to really speak of. So, having said that, let us move to this, that the formulation would involve generation of different cutting patterns and deciding which cutting pattern to choose and in how many numbers. Is it all right? Now, decision variables will thus be integers representing number of time a given cutting pattern should be selected, right. So, this could be another type of problem which we have to also take up. Then let us move over to the fourth type, which we may call a set covering problem. See, the overlapping services are offered by a number of facilities to a number of customers. Now, to find a set of facilities from among a finite set of candidate facilities, so that every demand node is covered by at least one facility. So, let us take an example. Suppose several medical emergency response units are to be located in a city, so that it can respond to calls within the city within 8 minutes of the call. The city is divided into 7 population zones. The travel time between the centers of each pair of the zones is known. The response units can be located in the center of population zones 1 through 7 at a cost. Is it all right? Now, formulate an appropriate set covering model to determine where the units are to be located and how the population zones are to be covered. So, that is the problem. You see, this problem will be better understood, if you really look at the matrix. You see, the matrix could be something like this, that you see, I have before us, say, supposing these kind of distances. Let us take only few distances. Really speaking, there will be 1 to 7 and here also 1, 2, 3, 7. So, there will be so many distances. So, at least some distances let us put. So, suppose this is 10, this is 8, this is 2 and then there are others, and this is 7. This one is 12, this one is 9, obviously 1 to 1 there cannot be anything. So, there can be 0 actually. Then this is 3 to 2, 2 to 3 is, let us say, 9 and 2 to 7 is 8, right. So, I think you can understand that these are zeros, they do not exist. Now, if these are some of my distances, then the question is that can I locate, supposing I locate our emergency response unit at 1, that is the first one. So, I locate it here. So, when I locate here, can I reach 2 within 8 minutes? Answer is yes. So, yes. Can I go to 3? Yes. Can I go to 7? Yes. Right. But from 2, can I go to 1? No. Can I go to 3? No. Can I go to 7? Yes. So, you see, I have given only some example that if I locate in 1, then I can reach 2, 3, 7, obviously others I have not discussed. If I locate at 2, I can reach 7, but not 1, 2, not 1 and 3, because they are not within 8 minutes of call. So, essential idea is that to locate the medical emergency unit at a given location, it does not cover all the units, is it okay? So, if I locate in 1, maybe it covers 2, 3, 7, but suppose there could be a 5 where it is cannot. Similarly, at 2, it does cover maybe 5 and 7, but it does not cover 1 and 3. So, it is not really a thing that I have to just locate at 1, then I will not be able to cover all. If I put in 2, again I will not be able to cover all, but if I put 1 at 1 and 1 at 2, maybe I will cover all, but then its efficiency may not be the best. Maybe if I choose 1 and 7 or 1, 6 and 7, my efficiency will be the best. So, where exactly I should locate my facilities so that my efficiencies will be the best? That is the essential idea of the set covering problem. I hope you understood, which is also an integer programming problem. Now, let us look at the different types of integer programming problems that we can have. It could be pure IP, where all xj's are integers. It could be binary, that is 0 or 1, right. That could be the second type, or it could be mixed. Mixed, there will be some xj's that will be 0, I mean greater than equal to 0, and they can take continuous values, or but the others, the rest has to be integers. Is it all right? So, we have pure IP, binary IP and mixed IP. In mixed IP, the rest could be integers or binary. Is it all right? So, these are the different types of integer programming problem, and we have discussed what is integer programming, how to formulate integer programming, that will be our next set of lectures, and later on how to solve them. So, with this I stop at this point. Thank you very much.